Hi, my name is Tunde. This is an explainer video to describe the steps taken in a machine learning experiment using Microsoft Azure Machine Learning Studio. What we have here is a classification problem, and we're given a data set that contains attributes about employees, and the goal is to figure out if uh, the goal is to predict if an employee will be promoted or not, given the data set. So the dataset here is represented by the module employee promotion.csv. And as with most machine learning tasks, it is important to explore the dataset first in order to build the most appropriate model to predict uh, labels. So we can here visualize what the dataset looks like. And as can be seen here, the data contains 54,000 rows and 14 columns, with each of the rows describing the features for a particular employee with a particular employee ID. You can see the department of each of the employee, the regions, the educational level, the gender, and so on and so forth. If you scroll to the right, you can see the column, which is actually what we want to predict, whether a particular employee will be promoted or not. Uh, for an employee that is being promoted, it's assigned a value of 1, and not promoted is assigned a value of 0. So this is essentially a binary classification problem, and we're just supposed to predict a 0 or a 1. Looking at the data sets, we can notice that there are some missing values, especially here on that previous rating, and some under the educational level. You can see in the previous rating column, there are about 4,000 missing values. This can be potentially problematic for machine learning because it doesn't know what to assign some of these values. So we have to be able to treat these missing values before we proceed with the data set. So the first task here will be actually to remove some of this missing data from the data sets. That's why here I have the cleaning missing data module, in which I select all of the features, which are all the columns of the data set. And my cleaning mode selected here is to remove the entire rows. Because the number of missing data is not as much as the entire data set, it poses no problem removing this entire rows with the data sets. Then if we look at the data set after running this module, we can see that the number of rows has reduced to 48,000 rows, implying that all of the missing data set has been removed. Another thing to notice is that the first few couple of columns are contain string data, which are just letters, masters and above, regions, sales and marketing. These are not numeric values, and it's difficult for machine learning model to use this in predicting some certain outcomes. So we're going to be converting all of these string values to categorical values, which means that each of the employees belong only to a particular category, either you're in sales and marketing department, or you're in an analytics department, or technology, and so on and so forth. So this is accomplished using the edit metadata module. In the edit metadata column, what is done here is to select all of the columns that have the string data sets, that have the string data types, and also KPIs met because and the previous year rating, because it ranges from 0 to 1, which is essentially a categorical type, and also previous year rating, which ranges between 0 and 5. So I pick only these columns to be categorical in nature. If you look at the results of this data set now, and you click on these columns, you can see now the feature types are categorical. But another important thing to do to this categorical feature is to convert them to indicators. Indicators implies that every feature, every category in this feature will have its own separate column, meaning education, which has 3 unique values, which is masters and above, bachelors, and one other category, which is probably below in this list, would have a different columns of themselves. So when I do this, I will be increasing the number of columns of the data sets. So I use the convert to indicator value, selecting all of the columns that I just mentioned, which are the department, education, gender, and recruitment channel, which are all string data types that I previously converted to categorical. And then I convert them to indicator values. If you look at the output of the indicator values now, you would notice that there's an increase in the number of columns that have been created. Previously, it went from 14 columns to 27 columns because the departments now have been split into the each of the categories within the department column. So we have legal, HR, finance, all of them representing a different column with one indicating that this is the column for this particular employee. Okay. After which, I select the columns in the dataset that I want to use from in my machine learning model. Here, I find out that it is not essential, or it would not be necessary to include the employee IDs in the prediction because essentially it does nothing. So I have selected here in the select columns that the employee IDs should be excluded from the data set. So what I have left is the remaining columns excluding the data sets. Then I move to normalize dataset. As you would see from the dataset as it was shown before, some of the values range, like the age goes from say 20 to 50, while some of them are ranging from 0 to 1 and thereabouts. So a particular feature that is used to mitigate against this difference in values is to normalize all of the data sets to a particular range. Here, I use the min max transformation method to make sure that all of the data lies within 0 and 1. Okay. So now the data cleaning of the feature engineering has been done. What we're then going to do before we pass this data to the machine learning model is to split the data between test and trained data. And here we're splitting them by the rows. 75% of the data is used to train the model, whereas the remaining 25% is to test how well our model is at predicting if an employee will be promoted or not. An interesting thing to see after you split the data, I can show the visualization here, is that our data is very imbalanced in the sense that we're trying to predict this column here. But if you look at the histogram of this column, you have more cases of not promoted, which is 0, compared to the number of cases that were promoted, which is 1. This is not very good when you pass it to your machine learning model because it learns more about the not promoted cases than the promoted cases. And one thing that can be done to make sure that we tackle this imbalance is to increase the number of cases of the promoted class. This can be done using SMOT. SMOT stands for synthetic minority oversampling technique, which increases the number of samples in the minority cases by a certain number of by a certain percentage. Here, I'm increasing the number of promoted cases by 600%, which means 6 times more representation, so that you can have some sort of balance between the non-promoted and the promoted cases. After that has been done, I can show what the data from this model looks like. You would notice that, just give it a moment. You would notice that now I have way more samples, 55,000 samples. And if I go to the column, is promoted column, you can see that now we have some sort of a closer balance between the non-promoted and the promoted cases, which is very useful in making sure that the machine learning learns very well both of the cases. So now I'm going to use a 2-class boosted decision tree algorithm to predict which of the cases to learn the cases. And instead of messing with the parameters that the trees can have, which is the number of leaves, the number of samples, the learning rates, I'm going to feed this algorithm into a tuned model hyperparameters. These values here are called hyperparameters of the model. But because I don't know what is the optimum parameter, if I run it into this model runs iteratively different values of these hyperparameters and figures out which one best gives me the result that I want. And here you can see I'm performing a random sweep using the twin model hyperparameters, and I'm using the F-score as a metric to determine which of the models will be best. So essentially, this figures out every hyperparameter that I need to produce the best model. This is then fit into the score model module to score the model and then evaluate how well it is performing on the test data. Another interesting thing that can be done is to see which of the features are actually most important in predicting which class it belongs to. If I show this, visualize, you would see that the average training score is the most important in actually predicting whether an employee will be promoted or not. Next is the department belonging to the sales and marketing department. the people belonging to this department probably would be this feature, the feature of people belonging to this department is important in actually figuring out if one is promoted or not. And after the whole model has been run, you can visualize the results and see that we have an F-score parameter of 0.547. You can you can see all the other metrics that one uses to evaluate the models, the accuracy, the precision, the recall, and so on and so forth. So basically, we've been able to train a machine learning model to determine if one is going to be promoted or not. Thank you very much, and I hope this has been informative enough for you.